Hello and welcome to Lore and Sleep. I'm really glad you're here tonight. Before we begin, if you're new around here, go ahead and hit that subscribe button, drop a like on this video, and let me know in the comments where in the world you're watching from tonight. I love seeing just how far this quiet little corner of the internet reaches. Now get comfortable, settle in, and let's begin. Tonight we travel upward, away from cities and empires and battlefields entirely, out past the rooftops and the treetops and the last scattered lamplight of the ancient world, into the one landscape that every single civilization this channel has ever visited shared completely and equally: the night sky above them, unowned by any king and unconquered by any army, the one part of the ancient world that genuinely, truly belonged to everyone who ever bothered to look up at it. We are going to look at the stars the way people looked at them for tens of thousands of years, before electric light ever existed to compete with them. A sky considerably darker and considerably busier with visible stars than almost anyone alive today has ever personally witnessed. And we are going to follow the patient, careful, centuries-long human effort to understand what exactly all of that scattered light actually was and what it might mean. This is the story of ancient astronomy, told not through the lens of any single culture or any single conquering empire, but as a genuinely shared human inheritance. Since Babylonian priests and Egyptian temple astronomers and Chinese court officials and Maya calendar keepers and Greek philosophers and medieval Islamic scholars all looked up, across many centuries and many thousands of miles of separation, at fundamentally the same slowly wheeling sky, and each, in their own distinct way, built systems of extraordinary patience and extraordinary mathematical sophistication to track it, predict it, in nearly every case, to weave it into their own deepest stories about the gods, the fate of kings, and the order of the world itself. It is a story about looking up, night after night, for years, and sometimes for entire lifetimes, simply to notice what moves and what does not, and about how much genuine understanding that kind of patient, unhurried attention can eventually produce. It is a story that belongs to the night in the most literal and most complete sense of anything this channel has ever told you, since its entire subject matter only ever appears after the sun has gone down, patient and quiet and utterly indifferent to whatever else was happening down here on the ground, while it slowly wheeled overhead. Let it come to you now, slowly, the way the first stars themselves always come, one at a time, into a darkening sky that only a few minutes before had still been full of daylight. But for now, there is nothing you need to do. Let your body grow heavy. Let your breathing slow. Let the stars themselves begin to come out above you, one by one, in a sky that has looked, in its broad outline, almost exactly the same for every human being who has ever lived, from the very first person who ever looked up and wondered, all the way down to you. Tonight, let us begin. For the overwhelming majority of human history, the night sky was almost unimaginably darker and almost unimaginably more crowded with visible stars than the sky that most people alive today have ever actually seen. Since the modern proliferation of artificial electric lighting, a technology barely a century and a half old, has produced a phenomenon astronomers call light pollution, washing out all but the brightest stars from the sky above. Virtually every modern city and town, a genuinely significant loss of ordinary human experience that means the sky ancient peoples looked up at nearly every clear night, a sky in which the Milky Way itself appeared as a genuinely bright, unmistakable band of light stretching directly overhead, and in which several thousand individual stars remained visible to the unaided eye, rather than the mere handful of the very brightest stars and planets that most modern urban observers can typically make out, is now, for most of the world's current population, a genuinely difficult thing to personally experience at all, without deliberately traveling to one of the shrinking number of locations still dark enough to reveal it. This considerably richer and considerably more immediate ancient experience of the night sky meant that celestial observation was not, for most of human history, a specialized or optional activity reserved for professional scholars, but rather an unavoidable and genuinely practical part of ordinary daily and seasonal life for essentially every human community. Since the sky provided, before any other reliable alternative existed, the primary available method for tracking the passage of time across the day, the month and the year alike, from the sun's own daily arc determining the hours to the moon's monthly cycle of phases, providing a natural calendar unit still reflected in the very word month itself, to the specific, carefully observed seasonal rising and setting positions of particular bright stars and constellations along the horizon, positions that shifted predictably across the year and that many ancient agricultural societies used as reliable practical markers for exactly when to plant, when to harvest, and when to expect the flooding of a river or the arrival of a particular season's weather. Polynesian wayfinding navigators, whose own sophisticated tradition of long-distance open ocean celestial navigation allowed the systematic settlement of the many thousands of scattered islands across the vast Pacific Ocean beginning many centuries before the Common Era, developed an entirely independent and genuinely remarkable practical astronomical navigational system, memorizing the specific rising and setting points of dozens of individual stars along the horizon, and using this detailed star compass, combined with careful attention to ocean swell patterns, wind, and the behavior of seabirds to maintain accurate heading and position across open ocean voyages of many hundreds or even thousands of miles without any of the written instruments or mathematical notation that the Babylonian, Egyptian, and Greek traditions this episode's later chapters will examine relied upon. An entirely oral, memorized astronomical tradition passed down through many generations of trained navigators that modern historians of navigation consider one of the most sophisticated pre-instrumental celestial navigation systems ever developed anywhere in the world. This same rich, unpolluted ancient night sky served practical navigational purposes considerably beyond mere calendar keeping, since sailors and travelers across virtually every ancient seafaring and desert crossing culture relied on the sky's own predictable, reliable patterns to maintain direction and position across open water or featureless terrain where no other reliable landmark existed. A practical navigational tradition this episode's later chapters will examine in specific connection with Polynesian and Arab maritime navigation, but that, in its most basic form, simply required a traveller to recognize a handful of consistently identifiable stars, particularly those close to the celestial pole that never set below the horizon at all, and to understand how their position in the sky related to the traveller's own direction of travel, a genuinely essential practical skill that made basic celestial literacy a matter of simple survival for anyone regularly traveling by sea or across trackless, desert terrain in the ancient world. Many ancient cultures developed what modern archaeoastronomers call horizon calendars, practical systems for tracking the changing seasonal position along the horizon where the sun rose or set on any given day, a considerably simpler and more universally accessible form of astronomical observation than the more mathematically sophisticated tracking of individual star positions that this episode's later chapters will examine in the specific contexts of Babylon, Egypt, Greece, China, and Mesoamerica, since a horizon calendar required only a fixed, consistently used observation point, whether a specific rock formation, a deliberately placed marker stone, or, in the case of built monuments like Stonehenge already discussed later in this chapter, a purpose-built architectural alignment, and the simple, patient, repeated observation of the sun's own gradually shifting, rising or setting position across the days and weeks of the changing seasons, a genuinely accessible and genuinely widespread form of practical astronomical observation that required no specialized mathematical training at all, only sustained attention and a reliably fixed vantage point maintained, in many documented cases, across many successive generations of the same community. The earliest surviving physical evidence for deliberate, organized human attention to celestial patterns considerably predates any of the great literate civilizations this episode's later chapters will examine in fuller detail, with archaeologists identifying possible astronomical markings on portable bone and stone artifacts dating back tens of thousands of years into the Paleolithic period, interpreted by some researchers as tallies tracking the phases of the moon, though the specific interpretation of these earliest and most fragmentary pieces of evidence remains, appropriately, a matter of genuine ongoing scholarly debate, given how difficult it is to establish definitive intent behind marks scratched into bone by people who left behind no accompanying written explanation of their own purpose. Considerably more architecturally monumental, and considerably more confidently interpreted evidence for organized prehistoric astronomical observation survives in the numerous megalithic monuments that Neolithic and early Bronze Age societies across Europe and elsewhere constructed, most famously Stonehenge on England's Salisbury Plain, whose massive standing stones, arranged in a careful circular pattern and erected in several distinct construction phases across a period stretching from roughly 3000 to 2000 before the Common Era, incorporate a genuinely well-documented alignment with the sunrise on the summer solstice and the sunset on the winter solstice, an alignment precise enough and consistent enough across the monument's careful stone placement that few modern archaeologists doubt it was entirely deliberate, even as considerable scholarly debate continues regarding the monument's fuller ritual, social and astronomical purpose beyond this specific and genuinely striking solstice alignment. This shared reliance on sustained, patient, multi-generational observation, a theme this entire episode will return to again and again across every single culture it examines, reflects a genuinely fundamental practical truth about astronomy that distinguishes it from many other ancient fields of inquiry. Since the sky's own genuinely significant patterns, the precise cycle of eclipses, the slow, subtle shift of the equinox points, the exact recurring period of a planet's own visible cycle, simply cannot be reliably detected within the working lifetime of any single observer alone, meaning that ancient astronomy, uniquely among most other ancient intellectual disciplines, structurally required exactly the kind of sustained institutional continuity, careful written record-keeping, and deliberate transmission of accumulated data from one generation of observers to the next, that this episode's remaining chapters will trace across Babylon, Egypt, Greece, China, the Maya world, and the medieval Islamic observatories alike, a shared methodological requirement that, whatever else separated these otherwise wildly different ancient cultures, quietly shaped each of their own astronomical traditions along genuinely comparable institutional lines. The particular human motivations driving this ancient, sustained attention to the sky were, in every culture this episode goes on to examine, genuinely inseparable from religious and mythological understanding, since ancient peoples living without any modern scientific framework for understanding what the sun, moon, planets, and stars actually physically were, had every practical and intellectual reason to understand these luminous, moving, yet clearly non-human presences in the sky as themselves divine, or at least divinely connected, a framework of celestial religious meaning that this episode's second chapter will examine in considerably fuller detail, and that shaped in ways both subtle and profound essentially every ancient astronomical tradition this episode will go on to describe. Nearly every ancient culture whose mythological traditions survive in any detail developed some considerable body of storytelling explaining the sun, moon, and prominent stars and constellations as gods, heroes, or significant mythological figures, a genuinely widespread pattern of celestial mythology that, despite considerable independent development across cultures with no direct contact with one another, reflects a shared human impulse to understand the sky's visible order through the same basic narrative and personal categories that ancient peoples used to understand the rest of their world, populating the heavens with recognizable characters and stories, rather than leaving them as simply abstract, impersonal points of light. The constellations that modern Western astronomy still uses today, and the specific mythological stories attached to many of them, derive substantially from ancient Greek tradition, itself considerably influenced by earlier Babylonian celestial observation and naming conventions that this episode's third chapter will examine in fuller detail, with figures including Orion the Hunter, Cassiopeia the vain queen condemned to circle the celestial pole in a punishing chair, and the various figures associated with the story of Perseus and Andromeda, all reflecting specific, well-documented Greek mythological narratives that ancient Greek astronomers and poets, including the 3rd century before the Common Era poet Aratus, whose astronomical poem Phenomena catalogued and described the constellations in verse form, intended partly as practical stargazing instruction and partly as literary entertainment, deliberately mapped onto specific patterns of stars, creating a genuinely enduring fusion of mythology and observational astronomy that later Roman, and still later medieval and early modern European astronomers largely inherited and continued to use with only modest further modification. A poem popular enough in its own era that the later Roman statesman and orator Cicero himself produced his own Latin translation of it, a small but genuine testament to just how widely this particular blend of careful sky observation and inherited myth-telling circulated across the wider educated culture of the ancient Mediterranean world. Egyptian celestial religion, which this episode's 4th chapter will examine in considerably fuller practical and architectural detail, centered substantially on the sun god Ra, whose daily journey across the sky in a solar bark, and whose nightly journey through the underworld represented one of the most central and most consistently depicted religious narratives in the whole of ancient Egyptian religious art and text, alongside the star Sirius, whose annual heliacal rising, meaning its first visibility rising just before dawn after a period of invisibility, was closely and reliably associated with the annual flooding of the Nile River upon which the whole of Egyptian agricultural civilization fundamentally depended, making Sirius, identified with the goddess Sopde, one of the single most practically and religiously significant celestial objects in the entire Egyptian sky. Andean astronomical tradition, developed by the Inca civilization and the various earlier Andean cultures that preceded it in the mountainous terrain of what is now Peru and the surrounding region, incorporated its own genuinely distinctive approach to celestial mapping, with Inca astronomers reportedly identifying dark cloud constellations within the dust lanes of the Milky Way in a manner conceptually similar to the Aboriginal Australian tradition already discussed in this chapter, recognizing the silhouettes of a llama, a fox, and other culturally significant animals in these dark, star-poor regions rather than exclusively connecting bright individual stars into figures, and the considerable astronomical alignment evident in Inca ceremonial architecture, including structures at the imperial capital of Cusco specifically oriented to track the sun's position at significant points across the agricultural calendar, reflects a genuinely sophisticated Andean astronomical tradition that, like the Aboriginal Australian and Maya traditions already discussed elsewhere in this chapter, developed in essentially complete independence from the astronomical traditions of Europe, Asia, and Africa that this episode's other chapters primarily examine. Norse mythology, developed across the considerably colder and considerably darker skies of Scandinavia, already discussed in this channel's own earlier coverage of the Viking Age, incorporated its own distinctive celestial narrative framework, with the sun and moon personified as the deities Sol and Mani, perpetually pursued across the sky by wolves whose eventual, prophesied success in catching and devouring them formed part of the wider apocalyptic narrative of Ragnarok, already discussed in that earlier episode. A genuinely striking example of how a specific culture's own wider religious and mythological preoccupations, in this particular Norse case a pervasive sense of cosmic vulnerability and eventual doom, could shape the specific way that culture chose to narrate even the most basic, universally observed celestial phenomena of the rising and setting sun and moon. Aboriginal Australian sky traditions, representing what many archaeoastronomers now consider among the oldest continuously maintained astronomical knowledge systems anywhere in the world, sustained across tens of thousands of years of oral tradition among Australia's indigenous peoples, developed genuinely sophisticated understanding of celestial cycles woven inseparably into what is generally called the dreaming, the wider Aboriginal cosmological and spiritual framework explaining the origin and ongoing order of the world, with specific documented traditions including careful attention to the heliacal rising of particular stars as seasonal markers for the availability of specific food sources, and a genuinely distinctive attention to dark, star-poor regions of the sky, including the dust lanes of the Milky Way itself, which several documented Aboriginal traditions interpret as the silhouette of an emu, a celestial figure defined by the absence rather than the presence of visible stars, a genuinely unusual and genuinely striking approach to constellation making that stands in notable contrast to the star-connecting approach that characterizes the Greek, Chinese, and other constellation traditions this episode's other chapters examine in fuller detail. Mesoamerican celestial mythology, which this episode's 6th chapter will examine alongside the Maya civilization's own remarkable astronomical mathematical achievements, developed an entirely independent but genuinely comparably rich body of celestial religious narrative, with the planet Venus holding particular significance within Maya religious and even military thought, since Maya astronomers tracked Venus's complex cycle of appearances as morning and evening star with such careful, sustained precision that Maya rulers reportedly timed certain military campaigns to coincide with specific, religiously significant phases of the planet's observed cycle, a genuinely striking example of how closely ancient astronomical observation and practical political and military decision-making could become intertwined in cultures where celestial events carried genuine, unquestioned religious authority, Chinese celestial religion and cosmology, which this episode's own 6th chapter will also examine in connection with China's remarkably long and remarkably continuous tradition of systematic astronomical record-keeping, organized the sky according to a somewhat different conceptual framework than the Greek and Mesopotamian constellation traditions already discussed, dividing the heavens into distinct palaces and enclosures associated with the earthly Chinese imperial court and its officials, reflecting a genuinely thoroughgoing Chinese cosmological conviction that the heavens and the earthly imperial government existed in a close, mutually reflective relationship, such that unusual celestial events, including comets, eclipses, and the appearance of new or unusually bright stars, were consistently interpreted by Chinese court astronomers as genuinely significant omens bearing directly on the fortune and legitimacy of the reigning emperor and his government, a system in which even the naming of individual stars and star groups after specific court offices and palace buildings reinforced, in the most literal and constant possible way, the conviction that the order of heaven and the order of the Chinese state were two expressions of the very same underlying cosmic principle. The ancient civilizations of Mesopotamia, the region between the Tigris and Euphrates rivers in what is now Iraq, produced what many modern historians of science consider the single most methodologically significant and most enduringly influential tradition of ancient astronomical observation anywhere in the ancient world. A tradition of careful, sustained, and remarkably long-term systematic skywatching that began already among the earlier Sumerian and Akkadian civilizations of the region, and that reached its most sophisticated and most historically consequential development under the later Babylonian and Assyrian empires during the first millennium before the Common Era. Babylonian astronomers maintained systematic written records of celestial observations across a period of many centuries, recorded on clay tablets in the cuneiform writing system already discussed elsewhere in this channel's own coverage of the ancient Near East, including a genuinely remarkable body of documents modern scholars call astronomical diaries, which recorded, on a regular and sustained basis stretching across several centuries, observations of the moon's position, the visibility of planets, weather conditions, and, alongside these purely astronomical records, notable contemporary political and economic events including grain prices and significant political developments, a genuinely unique historical resource that combines systematic scientific observation with incidental historical record-keeping in a manner without close parallel anywhere else in the ancient world. This sustained, multi-generational Babylonian observational tradition allowed astronomers to identify genuine long-term periodic patterns in celestial phenomena that would have been essentially impossible to detect through observation spanning only a single observer's own working lifetime, most famously the Saros cycle, a period of approximately 18 years and 11 days after which the Sun, Moon, and Earth returned to approximately the same relative geometric configuration, allowing Babylonian astronomers to predict the approximate timing of future lunar and solar eclipses with a genuinely impressive degree of practical accuracy, achieved entirely through patient long-term pattern recognition, rather than through any developed theoretical understanding of the actual physical mechanics producing eclipses. Since Babylonian astronomy remained throughout its history a fundamentally mathematical and predictive discipline, rather than a physically explanatory one, in the sense that later Greek astronomy would eventually attempt to become. Among the most significant surviving Babylonian astronomical texts is a compilation modern scholars call Mul, Arpin, named for its opening words meaning the plough star, a comprehensive astronomical compendium compiled sometime around the year 1000 before the Common Era, drawing on considerably older observational traditions and organizing a substantial body of practical astronomical knowledge, including star lists organized by the region of sky they occupied. Records of the dates on which particular stars became visible or invisible across the year, and practical rules for intercalating an additional month into the lunar calendar when necessary to keep it reasonably aligned with the solar year. A genuinely comprehensive practical astronomical reference work that later Babylonian astronomers continued to copy, use, and gradually refine across many subsequent centuries. Babylonian astronomy remained closely and inseparably connected to the practice of celestial divination, the interpretation of astronomical events as meaningful omens bearing on the fortune of the king and the state. The connection reflected extensively in the considerable surviving body of Babylonian omen literature, most notably a compilation called Enuma Anu Enlil, which catalogued many thousands of specific celestial observations, including particular planetary conjunctions, eclipse characteristics, and unusual atmospheric phenomena, each paired with a specific corresponding prediction regarding matters of state including military success, the health of the king, and the prospects for a good harvest. A genuinely extensive body of interpretive astrological tradition that provided the wider Babylonian royal court with continuous, professionally staffed astronomical advisory services and that, not incidentally, provided the sustained institutional and financial motivation underlying the systematic, centuries-long observational program that ultimately produced the genuinely significant scientific achievements, including the eclipse predicting Saros cycle already discussed earlier in this chapter, that modern historians of science most value from the wider Babylonian astronomical tradition. The zodiac, the specific band of 12 constellations along the sun's apparent annual path through the sky, that still structures Western astrology and that continues to inform the calendar names many people recognize today, formalized into its now familiar 12-part division sometime during the middle centuries of the first millennium before the Common Era. A systematic division of the sky that served Babylonian astronomers as a practical coordinate framework for recording and predicting the changing positions of the moon and the 5 planets visible to the naked eye: Mercury, Venus, Mars, Jupiter, and Saturn, against the background of more distant, apparently fixed stars, a genuinely foundational astronomical coordinate system whose basic structure, transmitted westward through Greek astronomy already discussed in this episode's 2nd chapter, and to be examined further in this episode's 5th chapter, continues to underlie both modern scientific astronomical coordinate systems and the popular astrological tradition, quite distinct from, and, importantly, not endorsed by modern scientific astronomy. The genuine sophistication of this accumulated Babylonian mathematical astronomical tradition finds a genuinely striking physical illustration in the Antikythera mechanism, an intricate ancient Greek geared bronze device recovered from a shipwreck off the Greek island of Antikythera and dated to sometime around the 2nd century before the Common Era, whose complex internal gearing, only fully understood through modern computed tomography scanning conducted many decades after its original 19th century discovery, reveals a mechanical astronomical calculator capable of modeling and predicting lunar phases, eclipses, and planetary positions according to cycles including the Babylonian Saros cycle, already discussed earlier in this chapter, a genuinely remarkable piece of ancient Greek precision engineering that directly incorporated inherited Babylonian astronomical mathematics into a mechanical calculating device whose own level of miniaturized geared complexity would not be matched again in European technological history for well over 1,000 subsequent years, standing today as one of the single most eloquent surviving physical proofs of just how thoroughly Babylonian mathematical astronomy had already been absorbed into the wider Hellenistic scientific world several centuries before Ptolemy would eventually bring that same inherited tradition to its own final, most complete systematic expression. Babylonian mathematical astronomy achieved a level of genuine predictive sophistication in its final centuries of development, particularly during the Seleucid period following Alexander the Great's conquest of the region, that considerably impressed and considerably influenced the subsequent Greek astronomical tradition, with Babylonian mathematical methods for predicting planetary positions, based on sophisticated arithmetic progression techniques rather than the geometric models that Greek astronomy would eventually favor, providing observational data and predictive techniques that Greek astronomers, including the considerably later Claudius Ptolemy, already discussed in this channel's own earlier coverage of the Library of Alexandria, explicitly drew upon and cited when compiling his own, eventually more geometrically sophisticated and more enduringly influential astronomical system. Ancient Egyptian astronomy developed along somewhat different practical and conceptual lines than the mathematically predictive Babylonian tradition already discussed, oriented substantially toward the practical, calendrical, and religious needs of Egyptian civilization, rather than toward the kind of sustained mathematical prediction of individual planetary positions that characterized Babylonian astronomical practice, with Egyptian astronomers focusing considerable attention on developing and maintaining an accurate annual calendar closely tied to the practical agricultural rhythm of the Nile's own annual flooding cycle, upon which the whole of Egyptian civilization's agricultural productivity fundamentally depended. The heliacal rising of Sirius, already briefly mentioned in this episode's second chapter in connection with its religious significance, provided ancient Egyptian astronomers with a genuinely reliable annual marker closely correlated with the beginning of the Nile flood season, and Egyptian civil calendar keepers developed, based on this observation, a 365-day civil calendar considerably more practically useful for administrative and agricultural planning purposes than a calendar based purely on the more visually obvious, but agriculturally less directly useful lunar month. Even though this Egyptian civil calendar's own lack of any leap year correction meant it gradually drifted out of alignment with the actual solar year across the centuries, a practical limitation that later Ptolemaic and Roman-era calendar reforms would eventually address. The considerable astronomical precision evident in the construction and orientation of ancient Egyptian monumental architecture, most notably the Great Pyramids of Giza, whose sides align with the cardinal directions to a degree of accuracy that continues to genuinely impress modern surveyors and archaeologists, reflects a considerable practical Egyptian astronomical and surveying sophistication, achieved, according to the most widely accepted modern scholarly reconstruction, through careful observation of circumpolar stars, stars close enough to the celestial pole that they never set below the horizon at Egypt's own latitude, whose nightly circular motion around the pole allowed skilled ancient surveyors to determine true north with genuine precision using relatively simple observational and measurement techniques, without requiring any of the more mathematically sophisticated methods that later astronomical traditions would eventually develop. The decans already briefly mentioned in this chapter's discussion of the Dendera zodiac ceiling deserve fuller attention here, since this specifically Egyptian system of 36 star groups, each rising heliacally at 10-day intervals across the year, provided ancient Egyptian timekeepers with a practical method for tracking the passage of the night into 12 rough hourly divisions by observing which particular decan star or star group was currently rising above the horizon, a system that Egyptian priests recorded in specialized star charts called decanal tables, painted or inscribed inside coffin lids and later temple ceilings, allowing modern Egyptologists to reconstruct this specific ancient Egyptian nighttime timekeeping system in genuinely considerable practical detail from these surviving physical artifacts. Egyptian astronomers and priests also developed practical instruments for daytime and nighttime timekeeping beyond the purely stellar decanal system already discussed, including shadow clocks, a simple but genuinely effective instrument using the changing length and direction of a cast shadow to divide the daylight hours, and water clocks, vessels calibrated to drain or fill at a steady, predictable rate, providing a method for measuring time that remained functional even when clouds or the specific circumstances of a particular religious ceremony made direct solar or stellar observation impractical. Practical timekeeping technologies that later Greek and Roman civilizations, this episode's 5th chapter will note, adopted and further developed from their own considerable prior Egyptian and Babylonian precedents. Egyptian temple architecture across the whole of the pharaonic period frequently incorporated deliberate astronomical alignments beyond the purely cardinal orientation of the pyramids already discussed, with several major temples, including the Great Temple Complex at Karnak, apparently aligned to capture sunlight along a specific axis during particular significant calendrical moments, most notably the winter solstice, an alignment that, when functioning as apparently originally intended, would have produced a dramatic, religiously significant illumination of the temple's innermost sanctuary at a specific and predictable moment in the annual solar cycle, a genuinely deliberate architectural integration of astronomical observation and religious ritual experience that later civilizations, including the Maya astronomical tradition this episode's 6th chapter will examine, would independently develop their own comparable versions of. Considerably older than the pyramids themselves, the megalithic stone circle at Nabta Playa in the Egyptian Sahara, dated by archaeologists to roughly the 5th millennium before the Common Era, predates Stonehenge, already discussed in this episode's 1st chapter, by well over 1,000 years, and its own careful arrangement of upright stones has been interpreted by several archaeoastronomers as incorporating a deliberate alignment with the summer solstice sunrise, a genuinely significant date in a landscape where that same solstice also marked, at the time this monument was built, the seasonal return of life-giving monsoon rains to what was then a considerably wetter Saharan region than the desert it would eventually become. Evidence suggesting that organized astronomical observation in the wider Egyptian and North African region considerably predates even the earliest dynastic Egyptian civilization that this chapter's remaining discussion primarily focuses upon, a genuinely striking reminder that the practical, observation-based astronomical traditions this whole episode has traced often reach back into a considerably deeper and considerably less textually documented prehistoric past than the more famous literate civilizations that eventually inherited and formalized them. The star charts and astronomical ceiling decorations that survive within several ancient Egyptian tombs and temples, most notably the famous astronomical ceiling of the tomb of Senenmut and the later, considerably more elaborate zodiac ceiling preserved in the Ptolemaic-era Temple of Hathor at Dendera, provide modern historians of astronomy with genuinely valuable physical evidence for exactly how ancient Egyptian astronomers organized and depicted their own understanding of the night sky's constellations and decans, a specifically Egyptian system of 36 star groups used to divide the night into hourly segments for practical timekeeping purposes, evidence suggesting a genuinely sophisticated and long-sustained Egyptian tradition of systematic celestial observation operating throughout most of its history, largely independently of the rather differently structured Babylonian and later Greek astronomical traditions already and still to be discussed in this episode's other chapters, a tradition whose own considerable practical achievements in calendar keeping, in monumental alignment, and in careful nighttime star-based timekeeping deserve to be remembered as genuinely significant in their own right, rather than merely as a historical prelude to the more famous Greek astronomical tradition this episode's next chapter now turns to examine in fuller detail. Ancient Greek astronomy underwent a genuinely significant intellectual transformation across the several centuries this episode's chapter will examine, moving from an earlier tradition considerably steeped in the mythological narrative framework already discussed in this episode's 2nd chapter toward an increasingly mathematical, geometrically modeled, an explicitly explanatory approach to understanding celestial phenomena, a transformation substantially associated with the broader Greek philosophical tradition's own characteristic drive to explain natural phenomena through rational, systematic inquiry rather than purely through mythological narrative. Even as Greek astronomy, as this episode's 2nd chapter has already noted, never entirely abandoned its inherited mythological constellation names and stories, even as its underlying explanatory framework grew increasingly mathematical and physically systematic. Thales of Miletus, traditionally credited as one of the earliest Greek natural philosophers, is reported by later ancient sources to have successfully predicted a solar eclipse that occurred in the year 585 before the Common Era, a claim whose precise historical accuracy modern historians of science debate, given the absence of any surviving contemporary Greek astronomical theory sophisticated enough to have genuinely enabled such a specific prediction, with many modern scholars suspecting Thales may have drawn, whether directly or indirectly, on the kind of accumulated Babylonian eclipse cycle knowledge already discussed in this episode's 3rd chapter, rather than having developed any entirely independent Greek predictive method of his own at this notably early stage of Greek astronomical development. Pythagoras and his considerable following of later Pythagorean philosophers, working during the 6th and 5th centuries before the Common Era, contributed the genuinely influential and, as it would eventually prove, remarkably prescient idea that the Earth itself was spherical rather than flat, a conclusion the Pythagoreans apparently reached substantially through aesthetic and philosophical reasoning regarding the sphere's own geometric perfection rather than through the kind of direct empirical observational evidence, including the curved shadow the Earth casts on the Moon during a lunar eclipse that later Greek astronomers would eventually marshal in the spherical Earth's own further support. And this same general Pythagorean intellectual tradition, considerably speculative in several of its specific cosmological claims, nonetheless helped establish the wider Greek philosophical expectation that the cosmos as a whole should reflect some form of underlying rational, mathematically describable order. Aristarchus of Samos, already discussed in this channel's own earlier coverage of the Library of Alexandria, in connection with his remarkably early proposal of a heliocentric model placing the Sun rather than the Earth at the center of the cosmos, represents, alongside the geometrically minded astronomer and mathematician Eratosthenes, also already discussed in that same earlier episode in connection with his own celebrated measurement of the Earth's circumference, one of the single most scientifically forward-looking figures in the entire ancient Greek astronomical tradition, even though Aristarchus's own heliocentric proposal, as that earlier episode already noted, failed to gain wide acceptance among his own ancient contemporaries and successors, who generally found the alternative geocentric model, placing a stationary Earth at the center of the cosmos, considerably more intuitively persuasive and considerably easier to reconcile with the ordinary, unaided observational experience of watching the Sun, Moon, and stars appear to move across a sky above an apparently stationary Earth, between the earlier Pythagorean speculation already discussed and the later, more fully developed geometric models this chapter goes on to examine. The 4th century before the Common Era astronomer and mathematician Eudoxus of Cnidus made a genuinely significant intermediate contribution, proposing a model of concentric, nested celestial spheres, each rotating on its own axis at its own particular rate, combined together to reproduce the observed motion of the Sun, Moon, and planets around a stationary central Earth, a geometrically ingenious system that Aristotle would later adopt and considerably elaborate within his own broader physical cosmology, and that represents the first genuinely mathematically rigorous Greek attempt to model planetary motion through a coherent physical and geometric system, establishing an important methodological precedent that the later, more sophisticated epicycle-based models of Hipparchus and Ptolemy, already discussed elsewhere in this chapter, would substantially build upon and eventually surpass in predictive accuracy. Hipparchus of Nicaea, working during the 2nd century before the Common Era, and already briefly discussed in this same earlier Alexandria-focused episode, in connection with his foundational contributions to mathematical astronomy, and his considerable direct use of the accumulated Babylonian observational record, achieved several genuinely significant additional astronomical accomplishments beyond those already mentioned, including the discovery of the precession of the equinoxes, a slow, gradual shift in the Earth's own rotational axis that causes the position of the celestial pole and the specific stars marking the vernal equinox to shift very gradually over a cycle spanning approximately 26,000 years, a genuinely subtle astronomical phenomenon that Hipparchus identified only through careful comparison of his own contemporary observations against considerably older Babylonian observational records spanning several preceding centuries, a further striking demonstration of just how much genuine scientific discovery depended, throughout the ancient world, on exactly the kind of patient, sustained, multi-generational observational record-keeping that this episode has repeatedly emphasized across several of its preceding chapters, the specific geometric machinery that Ptolemy's Almagest employed to achieve its genuinely impressive predictive accuracy. Despite resting on the ultimately incorrect geocentric premise, involved a sophisticated system of epicycles, small circular orbits whose own center itself moved along a larger circular orbit called a deferent centered on or near the Earth, a genuinely ingenious geometric device that allowed Ptolemy's model to reproduce the observed, sometimes apparently backward or retrograde motion that planets periodically display when viewed from Earth, a phenomenon actually caused by the Earth's own orbital motion around the Sun periodically overtaking or being overtaken by the other planets' own orbits, but which Ptolemy's Earth-centered model could only reproduce through this considerably more mathematically elaborate epicycle and deferent system. A genuinely impressive piece of mathematical modeling that, whatever its underlying physical incorrectness, allowed Ptolemaic astronomy to generate planetary position predictions of genuinely useful practical accuracy for well over 1,000 years of subsequent astronomical practice. Claudius Ptolemy, working in Alexandria during the 2nd century of the Common Era, and already discussed at some length in this channel's earlier coverage of that same city's famous library, brought this entire preceding tradition of Greek mathematical and geometric astronomy to its single most complete, most mathematically sophisticated, and, for well over a millennium afterward, most enduringly influential systematic expression in his astronomical treatise, known by its later Arabic-derived name, the Almagest, which presented a comprehensive geocentric mathematical model capable of predicting the observed positions of the Sun, Moon, and 5 visible planets with a genuinely impressive degree of practical accuracy. A model that, despite its underlying geocentric premise now known to be physically incorrect, would remain the standard authoritative reference for both Islamic and European astronomical calculation across the entire following medieval period. A subject this episode's 7th chapter will examine in considerably fuller detail. Chinese astronomical observation and record-keeping constitutes one of the longest continuously maintained traditions of systematic celestial observation anywhere in the ancient or medieval world, with Chinese court astronomers maintaining official astronomical records across a span of many centuries and, in certain respects, several millennia, motivated substantially by the cosmological conviction, already introduced in this episode's 2nd chapter, that unusual celestial phenomena carried direct significance for the legitimacy and fortune of the reigning imperial dynasty, a conviction that gave Chinese court astronomy a genuinely central and consistently well-funded institutional position within the wider structure of Chinese imperial government across many successive dynasties. This sustained, centuries-long tradition of official Chinese astronomical record-keeping produced what modern astronomers and historians of science consider a genuinely invaluable historical resource, since Chinese records preserve detailed, reliably dated observations of numerous significant astronomical events, including the famous supernova of 1054 of the Common Era, whose remnant modern astronomers now identify as the Crab Nebula, an observation Chinese court astronomers carefully recorded as a guest star, visible in daylight for several weeks, providing modern astrophysicists with genuinely precise dating information for this specific stellar explosion that has proven scientifically valuable for calculating the nebula's own subsequent rate of expansion. A striking example of ancient careful observational record-keeping providing genuine, still scientifically useful data many centuries after its original recording. Chinese astronomers also developed, across many centuries of sustained observation, a genuinely comprehensive and remarkably early catalogue of individual stars, with astronomers including Gan Day and Shi Shen working during the 4th century before the Common Era, credited with compiling star catalogues that considerably predate the comparable Greek star catalogue that Hipparchus would compile several centuries later, already discussed in this episode's 5th chapter. Though the specific surviving textual evidence for these earliest Chinese catalogues remains somewhat more fragmentary than the later, better preserved Greek astronomical tradition, complicating precise comparative dating and comparative assessment of relative astronomical sophistication between these two largely independent ancient astronomical traditions. The Maya civilization of Mesoamerica, already briefly introduced in this episode's 2nd chapter, in connection with their own distinctive celestial mythology surrounding the planet Venus, developed a genuinely remarkable independent tradition of mathematical and calendrical astronomy, achieving a level of practical observational precision in tracking the cycles of the Moon, Venus, and the Sun that modern historians of science consider fully comparable to, and in certain specific technical respects arguably more precise than, the contemporary astronomical achievements of the classical Mediterranean world. Despite the Maya astronomical tradition having developed in essentially complete isolation from any of the Old World astronomical traditions this episode's other chapters have examined, Maya astronomical achievement found its most sophisticated mathematical expression in the elaborate interlocking calendar systems Maya astronomer priests developed, including the 260-day ritual calendar called the Tzolkin, the 365-day civil calendar called the Harb, and the so-called long count calendar capable of tracking dates across periods of many thousands of years, systems whose underlying mathematics required a genuinely sophisticated astronomical observation to calibrate and maintain accurately, and Maya astronomers achieved a calculated value for the length of the Venus cycle accurate to within a small fraction of a day relative to the modern scientifically measured value, an achievement of sustained naked-eye observational precision that continues to genuinely impress modern historians of astronomy studying the considerable body of surviving Maya astronomical texts, most notably the Dresden Codex, one of the few Maya bark paper books to survive the widespread destruction of Maya written material that followed European colonization of the region, a considerable and painful loss of accumulated astronomical record-keeping that means the Dresden Codex and its few surviving companion texts represent only a small, precious fragment of what was very likely, at the height of Maya civilization, a considerably more extensive body of astronomical observation and calculation than the surviving evidence alone can now fully reveal. The astronomical achievements of the ancient Puebloan peoples of what is now the American Southwest, particularly at the considerable settlement complex of Chaco Canyon in modern New Mexico, active especially between roughly the 9th and 12th centuries of the Common Era, provide a further genuinely striking example of independently developed monumental astronomical observation in the ancient Americas, with the famous Sun Dagger petroglyph site atop Fajada Butte, where carefully positioned spiral rock carvings interact with narrow beams of sunlight passing between large rock slabs to mark the summer and winter solstices and the equinoxes with a precision that modern archaeoastronomers consider genuinely deliberate, alongside several major Chacoan buildings whose walls and internal room alignments appear to correspond to significant solar and, in a few more debated cases, lunar standstill positions, evidence of a sophisticated ancient Puebloan astronomical tradition operating in complete independence from the roughly contemporary Maya tradition already discussed earlier in this chapter. Despite occupying the same broader American continent, Chinese astronomers developed increasingly sophisticated mechanical instruments for tracking and modeling celestial motion across the many centuries of their own sustained observational tradition, including elaborate armillary spheres, mechanical models consisting of nested rings representing the celestial equator, the ecliptic, and other significant astronomical reference circles, used both as practical observational instruments and as demonstrational models, with the astronomer and polymath Su Song constructing, in the late 11th century, an elaborate water-powered astronomical clock tower incorporating a rotating armillary sphere and a mechanical clock escapement mechanism that some modern historians of technology consider a genuinely significant precursor to the mechanical clockwork that would eventually develop, independently and considerably later, in medieval Europe, a further instance of the genuinely global, independently developing character of ancient and medieval astronomical and horological technology that this entire episode has repeatedly emphasized across its many preceding chapters: the Nebra sky disk, a bronze disk inlaid with gold symbols representing the sun, a crescent moon, and a cluster of stars widely interpreted as the Pleiades, discovered in Germany and dated to approximately 1600 before the Common Era, ranks among the oldest surviving portable representations of astronomical knowledge anywhere in the world, predating by many centuries the systematic Greek constellation catalogues already discussed in this episode's 5th chapter, and its own careful gold inlay work, including 2 additional golden arcs added in a later phase of the object's use, that modern archaeoastronomers have interpreted as marking the specific range of sunrise and sunset positions across the solstices, suggests a genuinely sophisticated Bronze Age Central European astronomical tradition operating in the same general period as the later construction phases of Stonehenge itself. Further evidence of just how widespread and how independently developed careful astronomical observation had already become across prehistoric Europe, well before any of the literate civilizations this episode's other chapters examine had begun their own systematic written astronomical record-keeping. Stonehenge, already introduced in this episode's first chapter in connection with its well-documented solstice alignment, represents merely the most famous among a considerable number of Neolithic and Bronze Age megalithic astronomical monuments constructed across ancient Britain and continental Europe, with numerous other stone circles and alignments across the British Isles, Brittany, and elsewhere in Atlantic Europe displaying their own apparently deliberate solar and, in several cases, lunar alignments. Evidence of a genuinely widespread European Neolithic tradition of monumental astronomical observation, whose specific religious and social meaning, given the complete absence of any surviving written explanation from the cultures that built these monuments, remains, unlike the considerably better documented Babylonian, Egyptian, Greek, and Maya traditions already discussed in this episode's preceding chapters, a subject of genuine and likely permanently somewhat speculative modern archaeological interpretation. Following the rapid 7th and 8th century Arab conquests that established the Islamic Caliphate across a vast territory stretching from Spain to Central Asia, Islamic scholars inherited and, over the following centuries, substantially expanded upon the accumulated astronomical knowledge of the ancient Greek, Persian, and Indian traditions that fell within this new political and cultural sphere. A translation and scholarly expansion movement centered substantially on the House of Wisdom in Baghdad, already discussed in this channel's own earlier coverage of the Library of Alexandria in connection with its crucial role preserving and transmitting ancient Greek scientific texts, where scholars translated Ptolemy's Almagest and numerous other Greek astronomical works into Arabic, beginning a centuries-long tradition of Islamic astronomical scholarship that considerably refined, corrected, and in several important respects genuinely extended beyond the inherited Greek astronomical framework. Islamic astronomers established numerous dedicated observatories across the medieval Islamic world, institutions considerably more architecturally and institutionally developed than anything the ancient Greek astronomical tradition had generally maintained, with major observatories including the Maragay Observatory in Persia, established in the 13th century under the astronomer Nasir al-Din al-Tusi, and equipped with a substantial library and a coordinated team of astronomers conducting sustained systematic observation programs across many years, and the later Samarkand Observatory established in the 15th century under the Timurid ruler and astronomer Ulugh Beg, a genuine prince who chose to spend a considerable portion of his own reign personally engaged in astronomical observation and calculation alongside his professional astronomers, whose own personally compiled star catalogue, based on fresh, carefully conducted original observation rather than merely updating older inherited Greek positional data, achieved a level of precision that considerably impressed later European astronomers who eventually gained access to it. Islamic astronomers also drew considerably on the independent Indian astronomical tradition, alongside the Greek and Persian sources already discussed, with Indian astronomical texts, most significantly the 5th century work of the mathematician and astronomer Aryabhata, who had himself proposed that the Earth rotates on its own axis and had developed sophisticated trigonometric methods for astronomical calculation, translated into Arabic during the earlier centuries of the House of Wisdom's own translation efforts, meaning that medieval Islamic astronomy synthesized genuinely global source material, Greek, Persian, and Indian alike, into its own increasingly sophisticated and increasingly original observational and mathematical tradition, a genuinely cosmopolitan scholarly synthesis that reflects the wider cultural and intellectual openness of the medieval Islamic world's own considerable translation movement. Islamic astronomers made numerous significant technical contributions to observational and mathematical astronomical practice, including considerable refinements to the astrolabe, an ancient Greek astronomical instrument that Islamic astronomers and instrument makers developed into a considerably more sophisticated and more widely used practical tool for measuring the positions of celestial objects and for solving a genuinely wide range of practical astronomical and timekeeping problems, and the development of increasingly precise and increasingly critical mathematical challenges to specific technical aspects of Ptolemy's inherited geometric model, with astronomers including Ibn al-Haytham and later the so-called Maragay school of astronomers associated with al-Tusi developing alternative geometric devices addressing specific technical inconsistencies within Ptolemy's original system. Mathematical innovations that some modern historians of science have suggested may have influenced, through channels of transmissions that remain a genuine subject of ongoing scholarly investigation, the considerably later work of the European astronomer Nicolaus Copernicus, who would eventually propose returning to the heliocentric model that this episode's 5th chapter already discussed in connection with the ancient Greek astronomer Aristarchus. Islamic astronomy maintained, throughout the medieval period, a genuinely close practical relationship with Islamic religious practice, since accurate astronomical calculation was directly essential for determining the precise direction of Mecca, the Qibla, required for Muslim prayer from any given location across the vast geographic extent of the Islamic world, for maintaining the lunar Islamic calendar governing the timing of religious observances including the fasting month of Ramadan, and for determining the precise daily prayer times themselves, which are defined by specific solar positions requiring genuine astronomical calculation to determine accurately for any particular location and date, a set of genuinely practical religious requirements that provided sustained institutional and financial support for Islamic astronomical scholarship across many centuries and across the entire geographic breadth of the medieval Islamic world. The Persian astronomer Abd al-Rahman al-Sufi, working in the 10th century, compiled a genuinely significant and beautifully illustrated astronomical treatise known as the Book of Fixed Stars, updating and considerably refining Ptolemy's own inherited star catalogue through al-Sufi's own careful fresh observation, and providing, among numerous other significant contributions, what is generally considered the earliest surviving written record of the Andromeda Galaxy, which al-Sufi described as a small nebulous patch of light, an object modern astronomers now recognize as an entire separate galaxy lying well over 2 million light-years from Earth, though al-Sufi himself, working many centuries before any theoretical framework existed for understanding galaxies as separate stellar systems distinct from our own, could only record it as a curious dim smudge of light in a particular constellation, a genuinely remarkable piece of careful naked-eye observational record-keeping that continues to be cited today as one of the earliest documented human observations of an object now understood to lie almost inconceivably far beyond the boundaries of our own galaxy. A considerable body of Arabic star names that remain in active use within modern astronomical nomenclature today, including well-known bright stars like Aldebaran, Betelgeuse, and Vega, represents a further direct and enduringly visible legacy of this sustained medieval Islamic astronomical tradition, since European astronomers, drawing extensively on Arabic astronomical texts and star catalogues as European astronomical scholarship gradually recovered and expanded during the later medieval and early modern periods, frequently retained the original Arabic names for stars that Islamic astronomers had themselves carefully catalogued and precisely measured centuries earlier, meaning that anyone identifying these particular bright stars in the night sky today is, without perhaps realizing it, using vocabulary directly inherited from medieval Islamic astronomical scholarship, the European astronomical tradition that had, across the earlier medieval centuries, relied substantially on Ptolemaic geocentric astronomy, transmitted and considerably refined through the Islamic scholarly tradition already discussed in this episode's 7th chapter, underwent its own genuinely revolutionary transformation beginning in the 16th century, when the Polish astronomer Nicolaus Copernicus, drawing on mathematical considerations regarding the relative simplicity and elegance of different possible geometric models, and quite possibly, as this episode's 7th chapter has already noted, on ideas at least indirectly related to the mathematical innovations of the medieval Maragay school of Islamic astronomers, proposed a heliocentric model placing the Sun rather than the Earth at the center of the solar system, a genuinely momentous theoretical proposal published, according to a frequently repeated historical tradition, only in the very year of Copernicus's own death in 1543, sparing him from having to personally navigate the controversy his proposal would eventually generate. The invention of the telescope in the early 17th century, an optical instrument whose specific original invention modern historians generally credit to Dutch spectacle makers working around 1608, transformed observational astronomy more fundamentally and more rapidly than any single development since the ancient world's own earliest systematic skywatching, and the Italian astronomer Galileo Galilei's own systematic telescopic observations, beginning in 1609, produced a series of genuinely startling discoveries within just their first year, including mountains and craters on the Moon's surface, 4 moons orbiting the planet Jupiter, demonstrating conclusively that not every celestial body orbited the Earth as the traditional geocentric model required, and the phases of Venus, observational evidence that provided genuinely strong empirical support for the Copernican heliocentric model that Galileo himself had already come to favor on more purely theoretical grounds. The subsequent, genuinely contentious conflict between Galileo and the Catholic Church, culminating in his eventual trial and forced recantation before the Roman Inquisition in 1633, represents one of the most historically significant and most enduringly symbolic episodes in the whole history of the relationship between scientific inquiry and institutional religious authority. A genuinely complex historical episode whose full context, including the considerable political and personal factors, among them Galileo's own occasionally combative personal style and his complicated relationships with several senior churchmen who might otherwise have proven sympathetic allies, alongside the more purely theological ones that shaped the Church's specific response to Galileo's own particular publications and public statements. Modern historians of science continue to examine with considerably more nuance than the simplified popular version of the story, pitting a purely rational scientist against purely dogmatic religious authority, typically allows a version of events this episode notes carefully rather than repeating uncritically. Since the actual historical episode involved genuine complexity on every side that a simpler morality tale tends to flatten away, Tycho Brahe himself, already introduced in this chapter, in connection with the precise pre-telescopic observational data underlying Kepler's own subsequent mathematical breakthroughs, deserves fuller individual attention as perhaps the single most accomplished naked-eye observational astronomer in the whole of human history, maintaining, across several decades of sustained observation from his own purpose-built observatory on the Danish island of Hen, a level of positional measurement precision that considerably exceeded anything any previous astronomer, ancient or medieval, had achieved, using large, carefully constructed and carefully calibrated instruments of his own design rather than any telescope, which would not be invented until after his own death, a genuinely fitting final chapter in the whole long tradition of patient, careful naked-eye observation that this entire episode has traced from Babylon through Egypt, Greece, China, the Maya world, and the medieval Islamic observatories, since Tycho's own painstaking data, gathered through exactly the same fundamental technique of careful, repeated, patient looking that every single astronomer this episode has discussed relied upon, provided the essential empirical foundation without which Kepler's own subsequent mathematical revolution could never have occurred, the astronomical revolution that Copernicus initiated and that Galileo's telescopic observations considerably strengthened, found its own final, mathematically decisive confirmation in the work of the German astronomer Johannes Kepler, whose careful mathematical analysis of the exceptionally precise naked-eye observational data that the Danish astronomer Tycho Brahe had compiled across several decades of sustained pre-telescopic observation revealed that planetary orbits were not the perfect circles that both the ancient Greek astronomical tradition and Copernicus's own initial heliocentric model had assumed, but rather ellipses, a genuinely fundamental mathematical correction that Kepler formalized into 3 precise mathematical laws of planetary motion that would, later in the 17th century, provide crucial empirical support for Isaac Newton's own subsequent, still more fundamental theoretical breakthrough, the mathematical theory of universal gravitation, which finally provided a genuine physical explanation for why the planets moved according to exactly the elliptical mathematical patterns that Kepler had so carefully and so painstakingly derived from Tycho Brahe's own patient decades of careful naked-eye observation. The considerable modern loss of easy access to the genuinely rich, star-filled ancient night sky that this episode's opening chapter described has, in recent decades, prompted a genuine and growing modern counter-movement, with astronomers and conservation organizations establishing officially recognized dark sky reserves and dark sky parks in locations across the world, from remote national parks to entire small towns that have deliberately redesigned their own street lighting specifically to minimize artificial light pollution, preserving for modern visitors willing to travel to these increasingly rare protected locations something genuinely closer to the full, star-saturated sky that would have been an entirely unremarkable, everyday sight for every single ancient astronomer this episode has discussed. A modern conservation effort that reflects a growing contemporary recognition that this shared human inheritance of a genuinely visible night sky, so casually available to every ancient culture this episode has examined, has become, within just the last century and a half of rapid artificial lighting expansion, a genuinely endangered and increasingly precious experience. Amateur astronomy today continues, in its own modern form, a genuinely direct continuation of the same patient, careful, unhurried observational tradition this entire episode has traced across so many ancient and medieval civilizations, with contemporary amateur observers, equipped with telescopes of a size and optical quality that would have been genuinely unimaginable to even the most well-resourced ancient or medieval astronomer, continuing to make scientifically valuable contributions, including the discovery of new comets and the careful monitoring of variable stars and other changing celestial phenomena, work often carried out from ordinary backyards on ordinary clear nights by people with no professional astronomical training at all beyond their own accumulated patience and their own careful attention. A modern citizen science tradition that, in its own way, echoes the same sustained, multi-generational observational patience that produced the Babylonian eclipse cycles, the Chinese supernova records, and the Maya Venus tables this episode has already described in such considerable detail. The considerable astronomical tradition this entire episode has traced across so many distinct ancient and medieval civilizations, from Babylonian eclipse prediction through Egyptian pyramid alignment, Greek geometric modeling, Maya calendrical precision, and Islamic observatory science, ultimately converged through this specific sequence of European Renaissance and early modern astronomical breakthroughs into the foundations of the modern scientific understanding of the cosmos that continues to develop today, and the sheer continuity of human attention that this whole convergent story represents. Thousands of years of patient, careful, night after night observation by astronomers working in civilizations that, in most cases, never had any direct knowledge of one another's parallel efforts, each nonetheless converging, gradually and independently, toward an increasingly accurate understanding of the same shared physical universe, remains, for many modern historians of science, one of the single most genuinely moving examples available anywhere in the whole of human intellectual history of what patient, sustained, unhurried attention, continued faithfully across many generations, can eventually accomplish. And so we leave the ancient sky resting in its own enormous, unhurried darkness. We stood beneath the same stars that Babylonian priests recorded on clay tablets for centuries without ever knowing why the patterns they so carefully tracked actually repeated the way they did, patient enough across so many generations of careful record-keeping to notice an 18-year cycle that no single human lifetime could ever have revealed on its own. And we watched Egyptian surveyors find true north by patiently tracking a handful of stars that never set, and Greek philosophers slowly, painstakingly turn old myths of hunters and queens into genuine geometric models of a spinning, orbiting cosmos, epicycle by careful epicycle, until the whole system could finally predict, with real accuracy, exactly where a given planet would appear on a given night many years in advance, we crossed an ocean that none of these observers ever knew existed, and found Maya astronomer priests independently tracking Venus with a precision that would have startled their unknown counterparts in Alexandria and Baghdad alike. And we stood beside Puebloan sun watchers atop a New Mexican mesa, marking the same solstices with careful stone and careful light. We stood inside the great medieval observatories of the Islamic world, where astronomers built increasingly sophisticated instruments to correct and refine a Greek model that had already stood, largely unchallenged, for well over 1,000 years. And we watched Al-Sufi record a faint smudge of light in the night sky that no one alive then could have known was an entire second galaxy, whole and distant and unimaginably vast. And we watched, at the very end, a single Dutch spectacle maker's simple invention finally let one Italian astronomer see, with his own eyes, the mountains on the moon and the moons of Jupiter that centuries of careful naked eye mathematics had already, in their own patient way, been quietly pointing toward all along. And we sat for a while beside Tycho Brahe on his own island observatory, measuring the sky by hand, year after careful year, so that another man he would never fully agree with could finally get the shape of the planet's orbits right. These are human stories. The priests and the surveyors and the philosophers and the astronomer kings were human, standing in wildly different places speaking wildly different languages, looking up at exactly the same unchanging stars and asking, in their own time and their own words, essentially the same questions we still ask when we happen to look up ourselves on some clear, dark, unremarkable night. Questions about what all of it means and how long it has been going on, and whether anyone else out there is looking up at that same sky and wondering exactly the same thing we are. If this journey brought you some calm, you might like the video or subscribe to the channel or leave a small quiet comment below. It helps others find their way here, and every person who finds their way here is one more person sleeping a little more gently tonight, looking up, wherever they happen to be, at whatever small piece of that same old shared sky still happens to be visible from where they're resting. There is another story waiting for you on the screen. You can simply let it play and let the night continue and let the old world keep talking in its old slow voice. One patient observatory and one quiet sky after another, for as long as you care to keep listening tonight. But for now, there is nothing left to follow. The observatory is dark. The last tablet has been carefully set aside for the night, its careful marks left to wait, unread, until whatever apprentice or successor eventually comes to read them next. The stars themselves are still turning slowly overhead, exactly as they always have, exactly as they will keep doing long after this particular night, and every night after it has quietly come and gone. Let your jaw unclench. Let your shoulders drop slowly, gently, the way they drop at the very end of a long night's watch. Let your hands open slowly, the way hands open when there is nothing left to measure and nothing left to record until tomorrow night. Let your breathing find its own quiet rhythm, slow and steady, in and out, like the patient, unhurried wheel of the stars themselves turning overhead, ancient and unbothered and entirely indifferent to how long you have been watching them tonight. The same slow wheel that Babylonian priests and Egyptian surveyors and Maya astronomer priests all watched turn above their own very different lives, long before either of us ever came along to watch it too. Sleep well and good night wherever in this quiet world tonight's old story finds you resting, under whatever small patch of that same old sky happens to be turning quietly above you right now. However many clouds or city lights might be standing between you and it tonight,